So we're on chapter 6 for gases. So you might feel a little pressure about now. So what is pressure? Pressure is force divided by area. And gases exist. Gases push out pressure, and where that comes from actually is a little bit of momentum from each of the tiny gas particle. So each gas molecule or atom for something like noble gases push against the wall, and if you sum up all those atoms, all those molecules from all those collisions of the gas particles hitting the wall, that equals the pressure. So, of course, a single molecule or atom does not put that much force on something, but if you multiply it by a big number, like, I don't know, 6.02 times 10 to the 23rd, then you can get a measurable, sizable pressure. And as I mentioned before, it's a result of molecular collision. And the pressure has a couple things: the number that it's hitting, how big the container is, and how fast, or I'm thinking of momentum, also the mass of the particles, the average speed of the particles, and momentum, therefore. And the total pressure tells you a couple things. The more gas, the greater the pressure. Also, as volume increases, the concentration goes down. But if you decrease the volume, the concentration goes up. We'll go into that with the gas laws. That's Boyle's law here. So it'll also do with collisions. So let's talk about pressure and particle density. Basically, more gas particles, the more collisions, the higher the pressure. And the vice versa for lower pressure. Fewer particles, fewer collisions, less pressure. And we have this in our ear. We equalize our balance in our ear, and it's not equalized. I mean, you can hear it. You can feel it. Your popping of your ears. That's where part of our balance center is in our ears. So if you ever have an earache, for instance, I've had an ear infections before, and losing your balance is a common symptom. So barometer is something, it typically has mercury in it, but it's a way to determine ambient atmospheric pressure. And the average pressure of the Earth at sea level is about 760 millimeters of mercury, a little less than 30 inches. And that means that the weight, so the mass times the gravity of the Earth, if you look at the weight of the air going all the way up to the edge of outer space, about 60 miles, 100 kilometers in that range. If you take the weight of all that air, that equals to the same weight of about 760 millimeters of mercury. That's about 10 meters or 33 feet of water. So that's equivalent to all that. So mercury is pretty dense. So we use mercury because it's a liquid, it's very dense. So this here shows a mercury barometer right there, and atmospheric pressure at sea level is typically about 760 millimeters of mercury. For atmospheres, you might have heard the mercury is falling when that means it's raining. When it rains, the air pressure typically drops suddenly. So here's some other pressure units: pascals. That's the SI unit. It's a Newton per square meter. Pounds per square inch, or PSI, 14.7 PSI. Millimeter mercury, inches of mercury, and atmospheric pressure. And these are used also for, especially PSI, is used in many applications. And so 33 feet of water is equivalent to, an atmosphere is equivalent to 14.7 PSI. So if you ever wonder how, like, firefighters, they figure out how much pressure to put on something, like say you want to shoot water 100 feet, and they do it by about 15 psi for 33 feet of water. So that's 3 times 33. So it means you need about 45 psi of water pressure to shoot water up 100 feet, or you need that as much to pump water up a hill. So they use these pressures also for other applications in engineering and firefighting, for instance. So manometer, this is a way to measure gas inside of of an apparatus. We typically don't use these as much anymore. You can use them. These are more analog sort of measurements. We typically just use pressure probes, but it's typically a U-shaped apparatus, U-shaped manometer, and it's. I'll show you a picture. It's probably better to show you a picture. If you have this is the U tube. It's called a U tube because it's a tube in the shape of a U, the letter U. And then the height difference is the pressure of gas relative to atmospheric pressure. And so in this case, the gas is pushing down. So that means the pressure inside the vessel is higher than atmospheric pressure. And if it was the other way around, it would be lower. And other thing about this pressure difference, it's the difference. I mean, so if you get the height here in atmospheric pressure, the actual pressure inside the chamber is an atmosphere or whatever the atmospheric pressure, the ambient atmospheric pressure of where you're at. It's the ambient atmospheric pressure plus that height of millimeters of mercury. So that's one thing to note when you're doing the calculations and measurements for these. It's gauge pressure versus actual pressure. So like your tires work off of gauge pressure, meaning if your tire pressure is 33 psi, it's actually 33 psi plus the ambient pressure, which is 14.7 psi. Blood pressure, we also use millimeters of mercury for that, and here are the ranges for the different blood pressures. So if your blood pressure is 120 over 80, that means that that's the millimeters of mercury for the systolic and diastolic pressures. So let's talk about the different gas laws. Let's start with the simple gas laws, and we're looking at the relationships between these variables: pressure, volume, temperature, and number of moles. And Boyle's law, it's pressure and volume are inversely proportional, meaning if you increase the pressure, the volume goes down. If you decrease the pressure, the volume goes up. So when one goes down, the other one goes up, and vice versa. And this shows the inverse relationship. This looks a lot. Well, this is the function of y equals 1 over x. So of course, the asymptotes for that don't make as much sense in the real world. But for Boyle's law, there's a constant temperature and also amount of gas or moles of gas, and it's the inverse relationship. And here's a picture showing it as well. So you can see here that increasing the pressure will decrease the volume. So double the pressure, half the volume, and so on. And this is important for diving. So for every 10 meters, that's 33 feet of water for those of you that are familiar with feet rather than meters. 10 meters of water is equivalent to about an atmosphere of pressure. And so if you go down 20 meters, that means that the pressure, you have 2 atmospheres from the water and then 1 atmosphere from the atmosphere. So the total pressure in your lungs is 3 atmospheres of pressure. And this is important for a couple things. If you ascend too quickly, you can get a condition called the bends. And I guess we'll talk about that more when we talk about gases dissolving. The nitrogen can form bubbles in your joints. Also, your lungs could explode. So you need to exhale as you're ascending. So otherwise you might get in trouble, like you get injured. So Charles' law is volume and temperature are directly proportional. And also we come up with the idea of absolute temperature. And the unit we give it is Kelvin. It's really, it's the Celsius temperature plus 273.15. And depending on if your sig figs, if you want to keep the 0.15 or not, or round it to 0.2 or something like that, depends on how exact you want your calculation. So what is absolute zero? Well, you get to absolute zero, the absolute temperature. Temperature is defined by average translational kinetic energy. So temperature is a measure of kinetic energy. And average kinetic energy. And also I use the word translational. So there are three types of motion with atoms. They have translational, which means it moves in three-dimensional space. So if you're driving your car down the road, moving it down the road, that is moving in a translational manner. So how else? So or me, I'm walking. If I'm walking across the classroom, I'm walking in a very translational manner. How else can I move though? If I'm standing still, I can spin. That's known as rotational, and I can shake, and that's known as vibrational. So molecules can store energy via rotation and vibration. So there's other ways to store energy. So translational energy, though, that's moving in three-dimensional space. At absolute zero, there is no translational motion. And so that's why there is no such thing as beyond 0 Kelvin, because you can't go any slower than not moving. Are things still moving at 0 Kelvin? Yes, molecules can still vibrate, can still rotate at 0 Kelvin, but at 0 Kelvin they are not moving translationally. But volume and temperature via Charles' law are directly proportional. And I told you an application from this is the absolute zero idea. Of course, for real gases, as you approach absolute zero, the particles of the gas actually come into an issue. But 0 Kelvin, this is the zero volume for an absolute for ideal gas. It's also where all translational motion stops. And so let's look at this in terms of molecular views. So volume and temperature directly proportional. That means when you cool something off, the volume goes down. And then if you heat them up, the volume gets bigger. And this is in exactly the converse to Boyle's law that says that volume and pressure are inversely proportional. So this is the direct proportion. One goes up, the other one goes up, one goes down, the other one goes down. And that's opposite for pressure and volume. So, and I mentioned here, so since temperature means average kinetic energy, if you have higher temperature, that means that each collision that happens, the force is greater. So that's the point of that. The higher temperature, higher kinetic energy, higher momentum pushing on the wall. And and here is hot air balloon and also balloon shrinking. So volume and temperature, it's another part of it. Avogadro's law basically says the more number of moles of gas, the higher the volume. And this is how you blow up balloons. You put more air into the balloon inflates. That's Avogadro's law. And it's pretty straightforward, right? If you want to double the volume of the balloon, you put twice as much air. And okay, let's do this. Which action caused the volume of a gas sample to increase? Decreasing the pressure, yes, it does. That's Boyle's law. Decreasing temperature, no, that's directly proportional. Decreasing the number of moles, nope, that's not all. It's A. A is the one, that's Boyle's law. So here's the where we have right now. We have Boyle's law, Charles' law, Avogadro's law. And that means that volume is proportional to the number of moles times the temperature divided by the pressure. So we can write a general equation, and we're missing this alpha. Oh, we don't have alpha. It's using the infinity for proportion. The proportion, we can make it exact by including the value called the gas constant. Gas constant is actually Avogadro's number times the Boltzmann constant, so it's actually two different constants put together into one. But the idea here is a constant, and then now we have an equation. And we have the ideal gas law equation that fits all the other simple laws. Pressure times volume equals the number of moles times the gas law constant times the temperature. So it fulfills all the rules of the inversely proportion of Boyle's law, the direct proportion of Charles' law, and Avogadro's law. And we're not including Gay-Lussac's law. And we also have standard conditions. Standard conditions for gases, we say it's an atmospheric pressure at 0 Celsius. And this is different than the standard states that we'll talk about in thermodynamics. That's at 25 degrees Celsius. So the molar volume for an ideal gas at the standard temperature and pressure is approximately 22.4 liters of volume. And this means that we have a mole of gas, which means we have Avogadro's number of molecules of gas. And it doesn't matter what gas it is. It does not matter because for ideal gases, and later on we'll talk about the non-ideal gases, gases at this temperature and pressure, meaning at our ambient temperature and pressure, act pretty close to ideal. And we also call the volume of this 1 mole of gas as a molar volume. And it doesn't matter what the gas is, a mole of helium, a mole of xenon, a mole of methane at the standard temperature and pressure is in fact the same volume, or very close to the same, because we'll talk about real gases later. The density of the gas, density is mass to volume, and this varies, where the volume is more or less the same for different gases at standard temperature and pressure. For ideal gases, exactly the same, but it's not, and no gas is ideal. But the density, though, does change for different gases. And for instance, if you look at density of helium is 0.179 grams per liter, density of nitrogen is 1.25 grams per liter. So let's compare. So let's look at nitrogen. Compare this to water. Water at, at 0 degrees Celsius, we'll say it's just liquid water. Liquid water's density is about a kilogram a liter. It's 1,000 grams per liter. So roughly speaking, nitrogen gas, which is the major component of air, is about 1,000 times less concentrated than water. So water is pretty concentrated versus a gas, and this is by about a factor of 1,000. This is why it's so easy for you to move your arms through the air, but you go underwater and you try and swim. You can push yourself pretty hard forward. I enjoy swimming, for instance, and you can really push yourself by pushing against the water. And it doesn't really work as well with air. And the reason why is because there's about 1,000 times as much matter in water versus air. And but we've in previous lectures I mentioned buoyant force. So helium balloons, assuming that the container is small, if you put enough volume on it, helium balloons will float. And before mentioning the density, we can alter the the equation, and we can get the density of the gas as pressure times the molecular weight divided by the gas law constant times the temperature. And let's arrange these gases in increasing order of density. So that means that the higher molecular weight, so neon is about 20 grams per mole, chlorine is about 35.9 grams per mole, fluorine is 38 grams per mole, and oxygen is, once I say chlorine is 70.9, 35.45 times 2. Oxygen is 32. So we'd have to go with the lightest, neon, then after that is going to be oxygen at 32, then fluorine at, so it'll be 38, and then chlorine at 70.9, and that's that one. Molar mass of a gas. So we can determine the molar mass by figuring out the mass of the gas divided by the number of moles. And this is true for everything. I mean, doesn't have to necessarily be the gas, be a gas. It can be any substance. If we figure out the number, if we know the mass and we know the number of moles divided 2, you get the molar mass. And so this is not just unique to gases. You do it for all types of molar mass calculations. So let's talk about air. Dry air depends on where you're at. It's typically about 1% or so of water vapor, but you remove the water, and air is about 78% nitrogen, 21% oxygen, a little less than 1% argon, and relative trace amount of carbon dioxide. And there's other trace gases too. There's typically nitrogen oxides, for instance, and depending on where you're at, sulfur oxides, and there's small amounts of things like neon and xenon or helium and hydrogen. Not as much, but these are the major components of air. And there's much more carbon dioxide than hydrogen, for instance. There's not very much hydrogen in air. but it's there. I worked in ultra high vacuum in my graduate school days, and there's plenty of hydrogen in the vacuum chambers that comes from the air. It's hard to get rid of, and you can average it out to one gas if you want. Certain applications, sometimes it's typically more done in engineering, but from these we can calculate the different terms, like the different variables. Um, but that's more typically done in engineering applications. Partial pressure is also known as Dalton's law of partial pressure. Since ideal gas laws, we'll talk about ideal gases. Talk about it later with kinetic molecular theory, but essentially ideal gases don't interact with each other. So the pressures of ideal gases are just the simple addition of each one. It's like as if the gases are all independent. And this doesn't necessarily, it works for more than just pressures. It works for a number of moles, for instance. You just add them right up. And so the pressure of each N, so individual component is as such, just solving for pressure for the ideal gas law. And as I said before, you just sum them up, and then the adding up all the pressures equals the total pressure. And then likewise, you can sum the number of moles of different gases as well. So the different terms are all just cumulative additive, and they work perfectly. Perfect gas. Mole fraction. This is the number of moles of whatever component you're looking at over the total number of moles. For many engineering and other applications, sometimes law, like if you look at the Code of Federal Regulations, look at laws for these, frequently for a gas phase mole fraction, they use lowercase y. Lowercase x usually denotes liquid phase mole fraction. But if you see a y component, and if you're doing engineering work or legal work connected to engineering work, if you see a y component, that's more typically done. But the idea with the mole fraction is the moles of some component over the total component. And since for pressure is a directly proportional number of moles, gases are easy because if you know the pressure, you know the moles. And for mole percents, so you can go by mole percents as well, and 100% of everything. Nitrogen, for instance, has a mole percent of 78% or 0.78, and you can just sum them up going across. And so gas mixture contains an equal number of helium and neon. A total pressure mixture is 3 atmosphere. What are the partial pressures of helium and neon? If it's a equal number of moles, it's just a half of each. So it's just C. It's a half of both. And so what? Why do we care? Well, if you like diving and you are a scuba diver, you got to be careful with oxygen toxicity. So oxygen, if you go below a certain amount of oxygen, you can get to what's a stage called hypoxia. And if you go above, you can get to an oxygen toxicity. And I've never been very high in oxygen toxicity. People tell me that your heart's beating really quickly and you breathe very slowly. And that's your maximum at rest. So it can be a very strange sensation. So what? Well, many deep sea divers change their mixture, and frequently you get a large amount of helium and a small amount of oxygen, and their mixtures are usually called heliox. So you decrease the oxygen concentration. So that way, when you go down and under high pressure, you're not going to get as high a partial pressure of oxygen in your lungs, and then you won't get to oxygen toxicity. So you can collect gas. Well, one of them, common way, is to displace water, and one thing with liquids have something called the vapor pressure, and it's temperature dependent. So the vapor pressure is modeled as the pressure that the liquid exerts at the surface. What's really going on is a dynamic equilibrium where the solution, which is especially the solvent. The solvent particles are switching back and forth between the vapor phase and the liquid phase, and it reaches an equilibrium. And well, also the vapor pressure, the concentration of the gas above the liquid is known as the vapor pressure. Also, when the ambient pressure equals the vapor pressure, the liquid then boils. So we have these tabulated as well. So here is the vapor pressure diagram for water, for instance. So you have the different temperatures, and here's the different vapor pressures. And these are the measured vapor pressure for water. In future chapters, we'll talk about some of the semi-empirical models and how you can calculate some of these values. But these are the actual experimental data, and this is better than the modeled data. So let's do an example experiment here where you generate hydrogen gas with zinc and hydrochloric acid and you displace water, so you create a volume. But if you notice here, the volume of the hydrogen gas in that area also has water molecules. So when you do the calculations for these, you have to take away the vapor pressure of water to figure out how much hydrogen gas actually was generated. And chemical reactions. So when you have chemical reactions, similar. So one thing about chemistry, you can't forget everything we just learned. So stoichiometry still involves relation to the gas. So and of course, stoichiometry oftentimes works in moles, works with mass, works with moles. But we all go back to moles, and we also work with the chemical accounting. So all these still come into play. And then the products. Sometimes, if you noticed before, we would have products in moles, products in mass, products in number of molecules. Now, when you deal with gases, you can expand what you can have products. You can have products as number of moles. It can be pressure. It can be volume. There's all sorts of things. So chemistry only becomes more fun as you learn more about it, of course. So including these reactions, gases, you can also have partial pressures. So it's easy at standard temperature and pressure. But if not, we can work out other units and other temperatures and other pressures. The same idea, though, using dimensional analysis, you can get to use the variable that you want and keeping true to the chemical accounting. We move on to talk about kinetic molecular theory. Kinetic molecular theory is what the ideal gas law is based off of. The ideal gas law is a model. There's no such thing as an ideal gas. The closest to an ideal gas is helium, but it's still, there is no such thing as an ideal gas. And we have kinetic molecular theory based off of some postulates. And here are the postulates. The gas molecules are negligibly small. So that means the gas particles themselves, the average kinetic energy is a translational kinetic energy proportional to temperature in kelvins. That's the definition. That's not necessarily a postulate. That is a definition. And the collision with one particle or the other is completely elastic, which is another way of saying there is no attraction to particles, and they don't stick together after they hit each other. And this is a problem because at lower temperatures and higher pressures, they tend to become less elastic. Also, certain gases, they have attraction to each other. So ideal gas law works pretty well at high temperatures and low pressures. Low temperature and high pressure regime, the ideal gas law starts to break down. But we'll talk about the breakdown of the ideal gas law later. And gas particles are constantly moving. That's true unless it's at absolute zero. I mentioned that traction is negligible. Some molecules like to hold hands. And this is a problem because it seems like two gas particles become one instead. And now that union of two gas particles will then act ideally. So it seems like there's fewer gas particles than there actually are. And when they hit each other or the walls, they bounce off. And also there's lots and lots of empty space. And okay, we've already mentioned average kinetic energy, but it's the average speed, and we'll show you some pictures soon to show you the average speed. And keep on coming back to the completely elastic. There may be an exchange of energy, but there's no overall loss of energy. Well, that's true about the conservation of energy. So Okay, so an elastic collision is like imagine the perfect uh, collision between two billiard balls. The amount of energy go in and the momentum of each equals the momentum of the sum going out. No friction here. Of course, remember gases are moving in space, so I mean there's not going to be any friction with anything in empty space. An elastic collision, this is like two cars crunching together. They'll come together, they crunch, and they stick together. So that's an inelastic collision. So the nature of pressure is force per area, and the strict law is container of the force. We've already mentioned this. And now we're going to use the kinetic molecular theory to explain Boyle's law. And decreasing the volume forces the molecules into a smaller space, but then they create more collisions, thus increasing the pressure. Charles' law, the volume of the gas is directly proportional to the absolute temperature. And so that means when you increase the temperature, you increase the 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 energy, the kinetic energy and or momentum of the gas particles, and then that means that increase the pressure, so that means the volume goes up. Avogadro's law says the volume of gas is proportional to the number of gas molecules. If you have more gas molecules, it pushes on the container more, and then the volume must go up. Dalton law, the total pressure is the mix of the partial pressures. Well, according to Dalton's law, they in ideal gas law, they don't interact. So since they don't interact, it's like they're individual gases, and you mix them together, you just sum them up and go on from that. And so let's talk about this ideal gas law. Well, we just kind of can have them all together. You add all the different gases, and then the pressure is just the total force of all the gases coming in. And it's just adds together. And temperature and molecular velocity. Okay, so this is talking about the root mean squared. So velocity, it depends on how much you know physics. Velocity has direction, so has positive and negative direction. So what's an easy way to get rid of negative direction? You square it. So you square the energy, and then you take an average of it. And how do you get back to the individual? Take the square root of that. So you take the velocity, you square it, you take the average of that, and then you take the square root of it. And that's the root mean squared. And also another physics, another physics equation, kinetic energy is 1/2 times the mass times the velocity squared. So that's where the kinetic energy comes from, and the Na is just Avogadro's number. So that's just the physics equation there. And so what? Well, depending on the mass of the particle. So this is, if you look at this chart here, on the y-axis, you have the average number, well, the relative number of particles, and then the x-axis is the velocity. And for the more massive gases, the distribution is very narrow. For the lighter gases, the distribution is very broad. And so that means that, and this is it. This is the spread of them, and this is the root mean squared. The root mean squared are the peaks. So if you look at the peak of each of these, that is the root mean squared velocity of each of these gases. And so what? Well, you can see here is a distribution, and in future chapters we'll talk about kinetics and chemical reaction rates. So at different temperatures, the spread is going to change. I guess I should change slides. Oh, no, I guess we don't have that. So that means at a given temperature, you can have gas particles that have very high velocity, enough so that actually you can engage in a chemical reaction. So look at the combustion of paper, for instance. If you've seen really, really old paper, it looks like it's burning. And it looks like it's burning because it is. It's burning very, very slowly. The oxygen has a small fraction of the oxygen particles have enough energy to burn the paper. Of course, you light it put it under a flame, and the paper's gone in seconds to minutes, or it takes thousands of years at this temperature and pressure. And so we do certain things like if you go to the National Archives in Washington D.C., they keep the some of the documents like the original Constitution is kept in in a helium environment, so it does not burn even at this temperature and pressure. And they also don't let you take flash photographs of it too, because the light can damage the ink and stuff like that. So, and I already mentioned this. The kinetic energy average is the 1/2 Avogadro's numbers, mass times root mean velocity, or velocity squared. I'm sorry, not the root mean squared. This is the velocity squared. We use U for velocity for some reason in chemistry. And the kinetic energy average is 3/2 times gas law constant R times T temperature. And to make the units work for this, we have to use the R unit to be 8.314 joules per mole Kelvin. And the reason for this is are the units, because the mass, also the mass needs to be in kilograms, because a joule is a Newton meter and a Newton is a kilogram meter per second squared. So that means a joule is a kilogram meter squared per second squared, and you need to have that joule to the kilogram units to cancel between the mass and that, and then you take the square root of meters squared divided by seconds squared to get meters per second. So that's the reason why you need to use R. R is a gas law constant. You need to change the units. So to get the units to work out, and then the units of root mean squared velocity at the end are in meters per second. So it's a dimensional analysis unit argument for the R being that. And I mentioned this briefly before about temperature and distribution. So at lower temperatures, there's a more narrow distribution. At higher temperatures, there's a broader distribution. The application for this, of course, are chemical reactions. So that's an easy one. So that the higher temperature, you can have higher fraction of gases that have enough energy to engage in the chemical reaction. And but the cooler ones, it's interesting though. The cooler temperatures have a more narrow distribution, where the hotter ones have a higher distribution. And I should explain the graph. Excuse me. If you look at the graph here, the y-axis is the relative amount, and the x-axis is the velocity. And mean free path, I guess I make sounds in my head when I see these. I think of a gas moving in a box. I usually apply the pew 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 sound. It's this gas is running around, striking the walls, striking other gases, moving around, and it just moves around. And this the average distance between these different collisions, this is known as the mean free path. And the more particles you have, the mean free path decreases, because it's going to be a more frequent collision because of that. So diffusion and effusion. Diffusion is the molecules just spreading out from high concentration to low concentration. This is known as diffusion. It's also entropy driven. Entropy is disorder. It's a very common force that drives the universe. But there's a process where you have a tiny hole in a container, and then the gas escapes through that hole. This is known as a fusion. And both of all, the rates of diffusion and effusion are related to its root mean squared velocity. And at the same temperature, the lighter gases are going to diffuse and effuse faster. So the heavier gases are going to move more slowly. And so what? Why do we care? This is partially how we enrich uranium. So using uranium hexafluoride. But here's an image of a fusion. So you have a hole into the vacuum, and then if you have and the rate, if you have two different ones, it's the inverse. Remember that the root mean squared velocity is proportional to 1 over the molecular weight. So that means if you have rate A over rate B, it's the opposite of the square roots of the different one. This is Graham's law of effusion. And so let's look at this. The glass tube contains equal number of moles of helium and argon. After 5 minutes, half the particles escape through the hole in the glass. What are the relative amounts of helium and argon in the tube at 5 minutes? Well, it's going to contain almost all argon at that point in time. So because the helium goes out faster. So moving on, talking about real gases. So what are real gases? So we went for the kinetic molecular theory, talking about the perfect gas, the ideal gas, and the ideal gas has no attraction between gas molecules, but guess what? Real gases have attraction. And so what? Well, when gases have attraction, it seems like the number of moles of gases goes down because two gas particles are going to approach each other and they're going to like each other, and there's going to be attraction between them. And now it seems like those two units act like one. Gas molecules do not take up space, but they do take up space. Ideal gas law works well for low pressure, high volume relative to each other. But if you push enough pressure on a gas, then the actual particles have an issue, and then because of that, it pushes the volume slightly up. And so depending on low temperatures and high pressures, these assumptions are not as valid for the ideal gas. So you can see here with the ideal gas, the volume, the ideal gas volume, we have different there is slight perturbation. They're not exactly the same. So what's going on here? Well, there's real gases. And at low pressure, kind of mentioned this, at very high pressure, the gas particles become an issue, and then the pressure is slightly higher. So if you look at this chart here, on the left shows you the molar volume. I'm sorry, on the left. The y-axis shows the molar volume. The x-axis shows the pressure. And if you see here that the higher the pressure, there's more of a deviation from the ideal gas law, and that the argon's pressure, the molar volume, actually goes up a little bit. One of the ways around this was using the van der Waals equation. Truth be told, there are better ways to deal with ideal gases than the van der Waals equation. Van der Waals equation is actually very bulky because you have to solve it iteratively. There's different ones, like K's law is much easier, where it includes a compression factor. It's just a fudge factor. It's used. I'm an engineer. I'm a chemist and an engineer, and just some of these other semi-empirical models are much easier to use than the van der Waals equation. But why are we teaching the van der Waals equation then? Because it illustrates what an ideal gas is. We're not necessarily looking for many applications of real gases at this point in time. But if you go on and have to deal with real gases, there are way better ways of dealing with real gases than the van der Waals equation. But the van der Waals equation has certain corrections. For instance, so the volume has this correction factor. And higher temperatures, so high temperatures, the gases are nearly identical that of an ideal gas. This is true. High pressure, high temperature, because things are moving so fast, there's not enough attraction to slow them down. But low temperature, the pressure of the gases are lower because they stick together. They stick together, and two particles seem to act like one. And so we get around that by adding this correction factor. And so if you look at this chart here, we have pressure on the y-axis and temperature on the x-axis, and then looking at an ideal gas versus xenon. At lower temperatures, the pressure is lower than predicted because xenon is going to stick together, and we have this correction factor for the pressure. And you add them together to form the van der Waals equation for an ideal gas, and you have the correction for the intermolecular forces, correction for the particle volume, and it's just pressure plus the van der Waals, the constant A, times the quantity N over volume, number of moles divided by volume, that quantity squared, times the quantity volume minus number of moles times the van der Waals a factor B, that quantity multiplied together equals nRT. It's just like PV equals nRT, but then there's the corrections for the pressure and the volume. And these equations are difficult to solve because they need to be solved iteratively. That is if you're looking for number of moles or volume and so on. So this is unwieldy, so it can be difficult. So, and but most of the time, an ideal gas law, and it depends on the temperature and pressure. Ideal gas law works pretty well for many applications. And like I said, there's better ones than the van der Waals equation, but it works pretty well. And but the point of this, among other things, is to show you what ideal gas law is, what ideal gas is, and what ideal gas isn't, and what a real gas is. So we are at the end. Thank you for listening.